Neural network algorithms are all the rage these days, in fields like image and audio recognition, natural language processing, big data analytics, and decision making. That's because they can learn and adapt by tweaking their internal parameters based on training data. But the thing is, running these algorithms on regular von Neumann computers can be a challenge. It's called the von Neumann bottleneck. Most of the processors used today are based on the von Neumann architecture. It was first introduced by John von Neumann, a famous physicist and mathematician, in his report First Draft of a Report on the EDVAC, back in the 1940s. The von Neumann architecture has three main parts: the control unit, the arithmetic logic unit, ALU, and the memory unit. The memory unit serves as storage for both data and computer instructions. The control unit takes care of getting and putting this information in memory, and the ALU handles all the mathematical and logical operations on the data. The separation of memory and processing causes slowdowns when dealing with a lot of data. This is known as the von Neumann bottleneck. The quest for neuromorphic computing started in the 80s, with the goal of creating a more efficient, biologically inspired computing system. Today, this field has advanced with specialized hardware and software specifically designed for neuromorphic computation. These systems consist of interconnected artificial neurons, enabling distributed computing and in-memory processing, overcoming the limitations of the von Neumann architecture. My thesis is about joining a research team to make a neuromorphic system. For that, it is necessary to create an artificial neuron. Neurons are the building blocks of the brain, and the process of transmitting signals starts with the dendrites. The signals are then combined and processed by the soma and sent to the axon hill fork for thresholding. If strong enough, it moves to the axon and splits into multiple signals at the axon terminals. The team's plan is to amplify the signal from the presynaptic neuron, weighted with an artificial synapse, and combine the signal from multiple synapses into the integration circuit. Thresholding and output trigger happen just like at the axon hill fork. If the signal passes, it's stored at the cathode-anode timer and fired at the right time. The driver helps communication between neurons. My personal task will be to develop a Memristor-based artificial synapses. But what exactly is a Memristor? For over 100 years, we only knew of three basic passive circuit elements, until 1971, when Leon Shua theorized a fourth one, the Memristor. He found it while studying the math behind nonlinear circuit theory and exploring the relationship between voltage, current, charge, and flux linkage. Out of the 6 possible combinations, 5 were already known. 2 were defined by charge and flux linkage. The other 4 were defined by 3 passive elements: the resistor, capacitor, and the inductor. But Shua noticed the missing link between charge and flux linkage, and introduced memresistance to fill the gap. The memristor's relation between voltage and current is a Lissajous function, with 2 states and 2 transitions. The 2 slopes which show conductivity are the low resistive state, LRS, and high resistive state, HRS. The transition from a low to a high resistance state is called reset, and the opposite is called a set. In this master thesis, we'll focus on Metal-Insulator-Metal Memristors. The dominant theory behind their switching is the filament formation theory, where a conductive filament through the insulator layer reduces the device's resistance. Considering bipolar devices, the material stack starts off as is after production. Some devices may need an electroforming step, which involves applying a high-intensity voltage pulses in order to create defects. As we increase the voltage, we reach a certain value where the filaments are formed and the device switches, causing a set. When we decrease the voltage and reverse the polarity, we reach a value for which the filaments are destroyed and thus the device resets. With that, we bring our journey to an end. My goal for this master thesis is clear: to find the ideal materials, create, characterize, and simulate memristors in various arrangements. Our ultimate goal is to construct a functional artificial synapse that can be seamlessly integrated with our artificial neuron. Thank you for joining me on this exciting journey. Until the next time.